Hello, astro enthusiasts. Welcome back as we begin week 2 of our online learning experience this semester. We just finished exam number 2. Hopefully that went well for everyone. Almost everyone has taken it at this point. The average was pretty good. It was an 88%, which is not terribly surprising given the change in format. So hope everybody did well on that. There are still a couple of students who need to take it, so answers won't be posted until everyone has taken it, but once everyone has taken it, you'll be able to check what the answers were, if you did get 1 or 2 of them wrong, or more than that, when you took it. So this is moving on now. We are talking about stars. We have seen how we know many things about stars. We have, there we go, seen how we can determine things like star masses, star composition, star ages, star motions, star distances, lots of things like that. We have gone over how stars form. Chapter 22, which we're starting now, is taking us from the main sequence and figuring out what happens as those stars run out of hydrogen, and what happens to the centers of those stars, what happens to the outer parts of those stars, what is the post-main sequence evolution of stars look like. So let's get going with that. So here is our standard HR diagram again. We've got the high mass stars at the very top, obviously the low mass stars at the very bottom, and this is the main sequence. And stars will spend most of their lives on the main sequence. So I don't want to downplay the main sequence part of a star's life, because for any given star, it will spend most of its life on the main sequence. However, it's a fairly boring time of a star's life. It's not changing in mass or temperature. It's not changing in luminosity. Its position on the HR diagram is fairly fixed. And so we don't spend much time talking about it. Stars are burning hydrogen and helium happily as they're on the main sequence. It's what happens after they run out that becomes interesting. And we'll talk about that on the next slide. But first, I want to sort of differentiate. We're going to talk about these stars in 2 groups, low mass stars and high mass stars. And this does a decent job of talking about the distinctions between those 2. Low mass stars are those that have less than 2 solar masses. High mass stars are certainly greater than 8 solar masses. There's a lot of stars that are in between those 2, between 8 and 2 solar masses, but we're not going to be too interested in these particular stars, because some of them will follow the high mass and some of them will follow the low mass, depending on the exact characteristics of these stars. But where that exact dividing line isn't all that important. The sun, though, definitely is a low mass star in this classification, and anything, say, 8 solar masses and above, is definitely a high mass star. So that's sort of what we're talking about when we say high and low mass stars. Okay, so here we go. Running out of hydrogen. What happens? Star is sitting there, it runs out of hydrogen. What will happen to the sun? The details are very complicated. It takes very large computer programs with huge amounts of physics put in them to be able to say definitively what will happen, or at least a model of what will happen. But we can distill that down into a couple of different things. One that happens to the interior of the star and one that happens to the exterior of the star. The details, again, are very complicated, but the basics are this. The core contracts and heats. Hydrogen is still burned in the shell. Luminosity, we'll talk about the exterior in a minute. But first I want to basically go to this diagram, running out of hydrogen, and think about what actually happens in the star. So I'm going to go old school now. I tried the advanced iPad, nope, whiteboard, it didn't work very well. I'm going to try the old school actual whiteboard with webcam and see if this works any better. So we're thinking about a star. We've got the center of the star, and we've got the external part of the star. I've drawn more circles. That wasn't too bad. And the question is, where is the star going to run out of hydrogen first? It's not going to happen everywhere at once. It's going to run out of hydrogen in the place where nuclear reactions are happening the fastest. Where does that actually happen? That is the place in the star where it's the hottest and the densest. Where is that? That is the very center of the star. So where have you run out of hydrogen first? You have run out of hydrogen first at the very center of the star. Excuse me. So that's the point at which you're going to run out of hydrogen first. There is no more at that point hydrogen to burn at that very dot in the center of the star. What happens then? Well, there is no more energy to be generated at that particular point in the star. Energy generation and the outward flow of that energy is a major part of what's keeping this star up. Energy flowing outwards from the center is actually providing a pressure that keeps this star from collapsing in on itself. And when that energy goes away, we're not generating energy anymore in the center, that outward pressure goes away at the very part of the center part of the star. And so as the center just runs out of hydrogen and that fuel source, that energy source suddenly goes away, that region is going to get bigger and bigger, because after the very center of the star runs out of hydrogen, well, the immediately surrounding region, where it is a little bit cooler and a little bit less dense, will run out next, and then the region around that, and then the region around that. So what you end up with is a shell, this white region here, where it is still, there is still hydrogen, and you're still burning hydrogen into helium, and you're still generating energy in the shell. In the central dot, you're no longer generating high energy anymore, and there's now just helium there. All of the hydrogen is gone. What happens? Well, this particular region of the sun no longer has enough energy to support itself. That energy that was providing the pressure that was holding up the star is now gone. And so what's going to happen? Well, that region that no longer has this outward pressure is going to contract. It's going to get all of this weight that's pushing down on it from above. It no longer has the as much outward force of pressure, and so the entire star, the entire interior of the star, is going to contract a bit. And interestingly, so the central region is going to get actually hotter and denser, ironically. After it runs out of hydrogen, the center is going to get hotter, it's going to get denser, and as that material contracts, it's going to get hotter. Now, the region where we're still burning hydrogen into helium and in the shell doesn't have anywhere to go. And so as the central parts of the star shrinks, everything else has to shrink down on top of it. And so even this region, where there was still burning hydrogen into helium, also shrinks down. This entire region of the star shrinks down, compresses, gets hotter, and gets denser. What happens to the nuclear reaction rates when the temperature gets hotter and the density gets higher? They go up. And so, ironically, even though we've run out of hydrogen in the very center of our star, in this shell where we're burning hydrogen into helium around it, things have gotten hotter and things have gotten denser as this whole region contracted a little bit. And that actually makes it so that there is more energy being generated in the center of the star than there was before, because it's being done at a higher level at all the regions around the star where there is still hydrogen and it's hot enough to burn. In addition to that, all of this region gets contracted inward a bit. There are regions outside of that, that were outside of that, that again contract down on top of it, where there wasn't hot enough or dense enough to burn hydrogen at a steady rate before, that now all of a sudden are hot enough and dense enough to burn hydrogen. And so not only is this region where you were burning hydrogen before doing it at a faster rate, but you've got other regions, other mass of the star that contract down and now are hot enough to burn hydrogen and helium and generate energy. The net result of this is the backwards and unintuitive thing of this whole thing. You run out of hydrogen in the core, you actually generate more energy because all of the regions surrounding that region where you run out are burning it at a higher rate. And so you're using more luminosity, you're generating more luminosity at the center of your star. That more energy actually provides an outward push to the rest of the star. And so that increase in luminosity actually makes the entire outer part of the star. So the inner part of the star is shrinking and getting smaller. More energy is being generated. That energy has to get out. That energy is pushing the outer parts of the star outwards. And so this star will get more luminous and it will get larger physically.